Hi, welcome back. So we're going to look at Arrhenius plots today, and in the last set of lectures we looked at the Arrhenius equation. So the rate constant for a chemical reaction is A times by e to the minus activation energy over RT. And there's really two parameters here that control how fast the reaction is, or how big the rate constant is, and that's the pre-exponential factor, which has got something to do with how quickly the molecules collide together and the probability when they collide they're facing the right way. But more importantly, we've got this activation energy. So remember that when you've got a chemical reaction, you've got a barrier to the reaction. So you've got a potential energy versus time or reaction coordinate curve, and you start off here, and in order to get to the product side, you've got to make it over a barrier. So here's my reactants, here's my products, here's my transition state, and that energy that it takes to hop over the transition state we call the activation energy. So in order to speed up a reaction, we've got to lower that activation energy. In fact, in order to understand what's going on in a reaction, we have to be able to measure that activation energy, because that is a measure of how hard it is for the reaction to take place. So here's what we're going to do. We're going to go ahead and do a little bit of math here, and we're going to convert this equation into something that we can plot on a graph in order to find the activation energy. And we're going to do this by taking the natural logarithm of both sides, so that is ln. So that's going to give us, on the left-hand side, the natural logarithm of the rate constant, and on the right-hand side, that's going to give us the natural logarithm of the whole shebang, so a times by e to the minus activation energy over RT. And the reason we're doing that is one of the properties of logarithms is that if you take the log of a times by b, that's exactly equal to the log of a plus the log of b. In fact, that's one of the reasons logarithms were invented, because it makes it very easy to multiply numbers. Effectively, you just add logarithms. So that's going to convert the right-hand side to the log of a plus the log of e to the minus the activation energy over RT. And the second simplification we can do here is we can recognize that the e to the power of is the anti-logarithm. So when you take the logarithm of an anti-logarithm, essentially these two terms vanish, and you just get the minus EA over RT. So that allows us to complete the expression minus EA over RT. So this is going to be exceptionally handy. So it doesn't look that handy, but let me go ahead and rewrite this another way. So log of K is equal to minus EA over R times 1 over T plus the logarithm of A. So if you're like, well, that still doesn't look very handy, take a look at this. So if we write y equals mx plus b, this should be bringing back memories of math, and this should be bringing back memories of straight lines. So if you plot the natural logarithm of the rate constant on the y-axis, and you plot the inverse of temperature on the x-axis, then if the Arrhenius equation is correct, you should see a straight line with a slope of minus the activation energy over r and a y-intercept of the natural logarithm of a. So that's totally awesome, because now we can solve for these interesting things like the activation energy by plotting a graph and finding the slope. So let's see how that's done. So let's just rewrite that equation. So the natural logarithm of the rate constant is equal to minus the activation energy over r times 1 over t plus the natural logarithm of a. So we're going to go ahead and do a plot here. We're going to go ahead and we're going to measure the rate constants, and we're going to take the log of them, and we're going to measure the temperature, and we're going to invert them, and we're going to plot this data on a graph. And if the Arrhenius equation is correct, we will get a series of data points that all line up in a straight line. So that's looking pretty good. And we can use something like a spreadsheet, right, or a ruler and some graph paper to go ahead and measure two things: the slope of the line, which we can see is equal to minus the activation energy over r, and we can go ahead and we can figure out the y-intercept, which is going to be equal to the natural logarithm of a. So for instance, if we're only interested in the activation energy, which quite often is quite frankly the only thing we're really interested in, 99 times out of 100, that would be minus r times by the slope. So that's totally awesome, right? So this is what they call, this kind of plot is known as an Arrhenius plot. And it's done all the time in kinetics. So half the time, right, or 99% of the time, we just want to know what's the activation energy of a reaction, what's that barrier. And so we can measure the rate constant versus temperature, and we can plot log K versus 1 over T, and then that slope that we measure, right, is related to the activation energy. All we have to do is multiply it by minus the gas constant. So then we can learn about the energy barrier to a reaction. Why are we interested in energy barrier so much? Well, if we make the barrier smaller, we make the reaction faster. And so we can compare reactions and see which ones are faster, which ones have a barrier that's small versus ones that are large. All right, stay tuned.